In a previous video, we saw how a graph can be represented using an adjacency matrix. We saw that the basic operations required an order of n time or constant time, but the space that was required was n square, where n is the number of nodes in the graph, and if the graph is sparse, then that would require a lot of wastage of space. So a better way of representing these kind of sparse graphs is adjacency list. This consists of list of all nodes in the graph, and every node is then linked to its own list. Now the list of each node, it contains the names of all the nodes which are adjacent to a given node. So what will be the key advantages of using this adjacency list is that it can represent sparse graphs without wastage of space as compared to the adjacency matrix, and also adding new nodes in the graph will be easy and straightforward. This we will discuss in more detail once we take a look at what an adjacency list is. So take an example of this graph over here. So we have a node A and there are 4 nodes, so there is a list of these nodes and each node is connected to its own adjacency list. So for node A, we know that it is connected to node B and node C. So A is pointing to another node B, and this is now pointing to the other neighbor of A, which is C. Similarly, node B, it is pointing to node C because C is connected to B, and then it is also pointing to node D because there is an edge from node B to D, so these are neighbors. C is connected only to node D. So you can see very clearly that each node is storing only the information of its neighbors. It is not storing which neighbor it is not connected to. That information is not required. So it is not storing that information. If you see over here, this was the adjacency matrix over here, and if we saw this particular row, this row was just showing us the connections of node C. It showed us that this node C is not connected to node A, not node C. It also showed that node B is also not connected to node C. There is no self loop, and node C is only connected to node D. So this row actually showed us D connected to C, A and B not connected to C, and no self loop. So only this information was providing us the actual information. This information is redundant. Once we know that C is connected to node D, we know automatically that it is not connected to nodes A and B, and there is no self loop of C also. So the adjacency matrix was storing redundant information. That is why this adjacency list is keeping a list of only the nodes which are connected. So we'll come back to this example. Now we have this undirected graph over here. As in the case of directed graph, we can keep information of only those edges which are directed from one node to the other, but an undirected graph, an edge from A to B implies that B is a neighbor of A and A is also a neighbor of B. This was not the case in an directed graph. So now if we see the adjacency list of this particular graph, we see that B and D are neighbors of A and C and D are neighbors of B, A, C and D are neighbors of B. So we can create an adjacency list which stores only the information about the neighbors. It does not say which nodes are not connected. Once we know that A, C and D are connected with node B. That means B does not have any self loop. Otherwise, that would also have been present in the adjacency list. Now, suppose we have a graph which has edge weights also. Then the nodes in the list can be defined in such a way, the structure can be defined in such a way that apart from storing the data of the content, it can also store the weight in that particular node. So this is the way an adjacency list for a graph with weights, with edge weights can be created. So we know that node A has a neighbor B and the edge weight is 4. We also know that node A has a neighbor D with edge weight of 2. And you can work this out similarly for all the other edges, for all the other weights, nodes also. Now we come back to this question again, that the statement that adding new nodes in the graph is easy and straightforward. Compare this with an adjacency matrix. Suppose a new node was added to the graph. That would mean redefining this matrix and transferring all these data to the new matrix. Currently, this is a 4 by 4 matrix, assuming that n was 4. That means the number of nodes in the graph were 4. So the adjacency matrix was defined for size 4 by 4. Any new node that is added, that means n becomes now 5. A new matrix of size 5 by 5 would have to be created. All this data that is present over here would have to be transferred to this new matrix. What would be the changes that would be required if we are creating a new node and if we are using an adjacency list? It would simply require one more entry in this list of vertices and a list of nodes for this particular vertex. That would not require the existing list to be changed or modified or to be neglected. So this means that adjacency list modifications, if the graph is modified, this is much easier as compared to an adjacency matrix. Also, the space that is required is much less.